Assalamu alaikum guys, how you doing? Today I'm gonna be continuing the second part of design of short columns, and today we're gonna talk about the presence of moment or eccentricity in columns and how we are going to deal with that. As I said, the eccentricity can come from the column being actually a part of the frame, and we know in frames we have internal moments, and that will influence the column. Let's say if I have something like that, so this will have both an axial force plus a moment, and that will cause an eccentricity. And as you know from strength of material, which define eccentricity as being the moment divided by the axial force. Eccentricity could also come from lateral force, which again will create a moment for me, and that moment will again create an eccentricity. The other part is due to the actually the load being not physically the centroid of the column. So in this case, now this force B will have an eccentricity, and then now this moment is actually caused by the force not being concentric with the column. So this is what I call like a physical eccentricity, where the load is actually on the column but not loaded in the center. So how we are going to deal with that? So let's look at this cross section that we have here. So here I have an eccentrically loaded column. And let's go to some definitions. Now, epsilon ultimate again is the concrete strain crushing strength, which is about 0.003. Epsilon prime S is the strain in the compressive steel. Epsilon S is the strain in the tension steel, which we back in lecture, remember, we always insisted to be equal to the yield strain. Okay, here in columns, we'll see how we deal with that. Now, D prime is the distance from the extreme compressive fiber to the centroid of the compressive steel. C is, again, the location of my neutral axis. D is the distance from the extreme compressive fiber to the centroid of my tension steel. H, on the other hand, is that section dimension in the direction of my eccentricity. As you can see here, the direction of my eccentricity is this way. So again, with H being in the direction of the eccentricity. So now we know that the force in the tension steel is going to be area of steel times Fs, which is again the stress in the tension steel. In the compressive steel, we're going to have A prime S times F prime S. Again, Whitney's block apply for concrete. Then again, with this being 0.85 F prime C, and with this being A, then the compressive force in concrete is going to be 0.85 F prime C A times B. Okay, so now for that we can assume that the nominal force Pn is going to be equal to the compressive strength in concrete, which is 0.85 F prime C AB, plus A prime S times F prime S minus 0.85 F prime C, again because there's also this I'm taking out the effect of the concrete stress inside the steel stress, and I'm going to call that C prime S, with the tension force now being again negative to the compressive force, and that's going to be area of steel times Fs. So in other words, I'm saying that my nominal force inside the column is attributed to the strength of concrete, the force in concrete, plus the force in the compressive steel, minus the tension developed in the tensile steel. Okay, as far as the moment goes, well, again, my eccentricity is divided from the center of from the geometric center of the column, because here I have a symmetric column symmetry. in the reinforcement, and I will revisit that issue when I will talk about the unsymmetrical reinforcement. But for now, this eccentricity is defined from the geometric center of the column, which is at h/2. So the nominal moment is going to be equal to my nominal axial force times the eccentricity, which is, if I take each force individually, again, Cc is my compressive force, and I'm taking the moment of this compressive force, which is located at a/2. Okay, so this is my compressive force right here, and that's going to be a/2. If I know that this whole distance is h/2, again being my geometric center, then my moment is going to be h/2 minus a/2, which I just put in right here, times that Cc. Then I'm going to move on now to the compressive force by the compressive steel, which is C'(S). So if this distance is from here to here is d prime, then the distance that I'm talking about is going to be h/2 minus d prime. Moving now to the tension force, again I'm taking the moment about the center right here. So this is where I'm taking the moment about this axis. So in this case, if I know that this whole distance from here to there is d, then the moment is going to be t times d minus h/2, since d is bigger than h/2. So I use these two equations to find the nominal axial force and the nominal moment developed. Okay, so what does that mean? Since we know we have infinite possibilities of eccentricity, right, for each column, the eccentricity could be 0, which means I'm going to have pure axial force, right? And I could have a very large, we'll not call it infinite eccentricity, but let's say I have a very large moment, okay, and that will give me a high value of eccentricity, which means now my column is under pure moment, which means my column virtually is becoming a beam. So since I have so many possibilities, we draw something what we call a column interaction diagram, okay, because of the infinite possibilities that we have, or the combinations that we have. So in that interaction diagram, I will be drawing the axial force on one axis, which is here my Pn, and I'm going to put on the other axis my moment. So if I have 0 eccentricity, which means no eccentricity, my load is concentric, then I'm going to achieve the value of P0, which we talked about in the previous class. If my eccentricity is large, and I'm going to say infinite, then I'm going to have a pure bending problem, and that's going to be my pure flexure moment that we also talked about in previous classes. And anything in between is a combination of the two. So as you can see here, as long as my eccentricity is small, I'm going to have a compression failure, okay? And that's going to happen until I reach the balance point. And it's the same balance failure that we talked about, in which I have yielding of steel and crushing of concrete at the same time. So up to this point, all of this is compression. After that, the tension failure will start to develop, and then my eccentricity is going to be larger than my, what I call the balance eccentricity. And I'm going to have each interaction diagram for each, I guess, for each column load combination. So that's why this is what we call the interaction diagram. And I'm going to show you how to calculate one in this example. So I have a 30 by 50 centimeter column. It is reinforced with 4 phi 30, 1 in each corner. Okay, F prime C is equal to 28 megapascals. Fy is 420. Determine the following. So I want you to find me the balance load, balance moment, and balance eccentricity. Okay, that's the first requirement. The second requirement, I would like to know the load and moment for a representative point in the tension failure region. Third requirement is the load and moment for a representative point in the compression failure region. I would like you to find the axial load strength for zero eccentricity. I would also like you to find the pure bending moment M0, and then I want you to sketch the strength interaction diagram. Okay, so let's start with the first requirement is finding the balance force. So let's first of all look at this cross section right here. Again, here is the application of my axial force, which now here notice this is going to be now my H, which is 50, and this is my B, which is equal to 30 centimeters. Okay, again, this is in the direction of my eccentricity. Here I'm giving you D prime equal to 6.5 centimeters directly, and I'm not asking you to calculate it. So here D prime is given, and it's the same from the other section, so we can actually calculate D from it. Okay, and D is just simply going to be my 50 centimeters minus 6.5, and it's going to be 435 centimeters. So first of all, I need to calculate my neutral axis for the balance condition, which is again the same technique that we used for flexure, and this is going to be D times epsilon ultimate divided by epsilon ultimate plus epsilon y, or the yield steel. D is 435. Again, this is just simply being 500 minus 65. This is going to be 0.03, my crushing, and this is also going to be 0.03. Here, for some reason, I used 0.02. You could, again, like I said before, either use this one or use 0.0221. Okay, so from that I found my CB to be 255.8 millimeters. From that I can calculate the A value, which is simply beta 1 times CB, and since F prime C is 28 and less, then my beta 1 is going to be 0.85. From that I found A to be 217.5. So from it I can calculate now the F prime S. Again, I know that the balance point is where my tension steel is yielding, so we already know that. But what we don't know is whether the compression steel is yielding or not. Okay, so to do that, use again the same equations that we used before, which is the ultimate strain times the modulus of elasticity, C minus D prime over C, crushing epsilon ultimate 0.003. This is my E for the steel. Again, this is the C that we just calculated, the CB, minus D prime, which is 65 divided by CB, and the value is 447, which is more than 420, which means that my compression steel has yielded. Okay, so from that I could actually calculate now my balance axial force, which is going to be my 0.85 times F prime C times A times B, okay, which is again 300. This is actually representative of 2 phi 30, okay, which are those right here. Okay, these are my compressive steel. Again, since the load is in this direction, since the load is here, so all this is under compression and all that is under tension. Okay, so this is again the 2 phi 30 that's all under compression. So times Fy, again we proved that to be yielding, minus 0.85 F prime C, now minus the tension force. Again, these are those two right here, 2 phi 30 times 420. So this is now my balanced force, axial force. So now I found the balanced axial force. Now I need to find the balanced moment, and again it's the same equation that I've shown you before, which is going to be 0.85 F prime C A phi B, and that's what we called CC, H over 2 minus A over 2, A prime S, and we called that C prime S, and then that for us was the tension. Okay, so CC is 1500 52.95, H over 2 is 0.25, A over 2, which is we just calculated, which is again the A balance. Okay, C prime S is the A prime S, F prime S minus 0.85 F prime C, which will give me a value of 560.12. H over 2 is 0.25, and then D prime is the 6.5 centimeters. Tension, again, this is AS times FS, but again, here this is equal to Fy, okay? And this also is equal to Fy, F we proven previously that they were yielding. So from that, I calculate the moment to be 432 kilonewton meter, which will give me the balanced eccentricity of M over P, which is about 0.285 meters. So that takes care of my first requirement. Now, the second requirement is telling me that he wants to have a point in the tension failure region. So I'm claiming that any choice of C less than CB will give a point in the tension failure region, and that's correct. So if I look at my cross sections, so my CB is somewhere here. So if I go in this direction, I will increase the area of tension and decrease the value of compression. If I go in that direction, you will increase the area of compression and decrease the area of tension. So this is again the tension area, so this will become less and less, and this will become more. So that's why when I choose a C more than CB, I will have more of a compression failure, and if I choose a C less than CB, I will have a failure more on the tension side. So since I'm choosing C to be 120, so this is the given value, I still like to find out if my compression steel yielded or not, so I can calculate F prime S directly, which is simply the crushing strain of 0.003. E again is 2 times 10 to the 5. C is the chosen value that I picked, which was 120. D prime is my 65, and I'm getting a value of 275, which is less than 420, which means my steel did not yield in the compressive part. But I do know, obviously, because I'm in the tension failure, so the steel in the tension is obviously yielding. If you don't believe me, you can go check it as we did before. So calculating now the axial force, it's going to be simply 0.85 times F prime C times 102, which is my A, which is actually equal to beta 1 times 120, which we chose, times B. This is my 2 phi 30, just to remind you. This is my F prime S, the 275, and this is the 0.85 times F prime C, minus the tension force times Fy again. So this is Fy, and this is my 2 phi 30 as we said before. Then moment, use the same equation as well. Again, this being my CC, this being my C prime S, and this being my tension force. Okay, so I'm just plugging that in. Still H over 2 minus A over 2, H over 2 minus D being my moment arms, and D minus H over 2. From that, I calculated my nominal moment to be 320.47. Divide the moment by the force, and I'm getting an eccentricity of 0.655. As you've noticed, that eccentricity is larger than the eccentricity for the balance condition, which is expected, because we said after the balance, the eccentricity will become more and more. For the third requirement, I'm going to choose a value of C again that it is more than CB, and here I've chose this to be 440 millimeter. Here I'm not giving you the details because I want you to go back and calculate the value. Just to have one note here, you notice that FS now has a value of minus 6.82, which means now that my tension force is now becoming a compressive force, okay, and which is obvious because D is at 435, which means that the whole steel, which I designated first to be as my tension steel, is now under compression. Hence, I'm getting the value of minus 6.82. Obviously, the compressive steel has yielded way more than it's supposed to be. But again, we never use a value more than the yield of steel. So in the equations, don't use 511. Actually, use 420. From that C, I was able to calculate A to be 374. I calculated my nominal axial force to be 3,240, the moment to be 270, and my eccentricity is going to be the moment divided by the axial force, which is going to be 0.0834. Again, you notice that this is less now than my EB, which again saying is I'm on track. I'm more into a compression failure than anything else. Now, as far as the requirement where he wants the axial force, or the pure axial force, then there's no eccentricity, and I'm just going to use simply value 0.85 F prime C. Here's my gross area minus the area of steel. Remember, this was 2,530. So if I multiply that by another 2, it will come to 4,530, plus the Fy times, again, the 4,530. So this is now my P0, which is about 4,600 Newton, 0.23 kilonewton. Just want to see how much the eccentricity is actually influencing your axial capacity. So this would tell me that the axial capacity is around 4,500. A small eccentricity like 0.08 knocked that down about 1,500 kilonewton. So that shows you how much small eccentricity can really influence the axial capacity of your column. Now for the requirement where I need pure bending. So for pure bending, large eccentricity, there is no axial force, so my P is going to be 0. So if I go back to this equation right here, I'm going to make this go to 0, which means my tension force now is going to be equal to my compressive force in the steel plus the compressive force in concrete. So the question that I need to answer, does the compressive steel yield, has it yielded or not? Now, if I am assuming that it has yielded, and since this is a symmetrical column, then the area of steel in tension is going to be equal to the area of steel of compression, which means that T is going to be equal to C prime S, which means that C sub C, or the compressive steel, will yield to 0, and we know that this is not right. So that obviously means that my compression steel did not yield. So for that, I'm going to use this equation again. I'm going to assume, well, the tension is area of steel times Fy. We know it's yielded. Again, because we're talking about pure moment right now. A prime S, F prime S, this is the unknown value to me, minus 0.85 F prime C plus 0.85 F prime C A phi B times B. Since I have a value of A here, I would like to use the equation for F prime C that I used before. And instead of C, I'm going to use A over beta 1. So I have one unknown in the value of A. If I do that, I will get a quadratic equation. I will solve for A, and now this is the solution for A, where Q1 is equal to this, and Q2 is equal to that. Okay. Again, since these equations will be made available to you during the exam, so you don't have to really worry about them. So calculating now Q1 based on the information that I have, and Q2, I found A to be 67.016 millimeters. From that, I was able to calculate the F prime S to be 105.34. Again, proving the point that the compressive steel did not yield. Now I can actually use the moment that I used back in flexure, which is 0.85 F prime C D minus A over 2 plus A prime S F prime S phi D minus D prime, or you just could also use AS Fy D minus A2. Doesn't matter because they're. Anyway, this is now my, no, I take that back. So M0 is equal to this right now. So from that, I was able to calculate my M0 to be 234.76 kilo newton. So now I'm ready to actually draw my interaction diagram. So what I did right here, okay, I did use more than obviously the 4 points that I did in the example. I actually generated an Excel spreadsheet to come up with this curve. So this value right here is my P0. This value right here is my M0. This is the one that we calculated when we assumed C to be equal 440. And this is the value where we assumed C to be equal 120. Okay, so this one gave me the eccentricity of 0.083, and this is equal to 0.65. So this is the interaction diagram that I'm drawing. Now, we usually don't obviously deal with the nominal, so we usually deal with phi, Pn. So in that case, I need to multiply that curve by 0.65. Okay, so now this is, just let me erase this. So this is the phi Pn, in which case I'll multiply that by 0.65. We also have an additional condition in which P0 must be also multiplied by 0.8 if it's a tight column, and we have a tight column. So now this is the area where it's going to be 0.8. Okay, so this is multiplied by 0.8. So you can see that because we cannot use anything above 0.8 P0. So anything above 0.80 we are going to disregard. So this is now the maximum value, or what I call the Pn max. To make things even worse, here since I have a tension failure, and I'm going to have a transition, okay, from compression to tension. So this is the phi T phi, which is again going from 0.65 up to 0.9. So the actual interaction diagram approved by the ACI code is going to be actually this diagram here, which is kind of messy, but nobody uses that, and we're going to use something else, which I'm going to introduce to you right now. Is called the dimensionless interaction diagram. Imagine if we have to do this for each column design, and this will become very, very tedious. So enter what we call the dimensionless interaction diagram. This is a tool that I can use for the design of columns, and they're actually quite there's a software out there that you could use. There is a column handbook, and it's a very thick handbook. So one of the things that you need to know. So here I'm showing you the interaction diagram that I generated using my Excel spreadsheet. First of all, if we go to the axis, which was attributed to the axial force Pn and to my moment Mn, you notice I normalized that with respect to F prime C area gross, okay, and that I'm calling Kn. So if you divide Pn by F prime C area gross, you're getting a dimensionless value, okay. Now, but since I'm not dealing with the nominal force, I'm dealing with the ultimate force. So usually we'll have the combination of, like we did before, 1.2 dead plus 1.6 life. So I'm going to use P ultimate and divide that by phi, which is going to be my 0.65. Okay. Now, if I go to the moment part, you guys see the dimensionless number here, right? Because F prime C area gross, F prime C is in, let's say, kilonewton per meter squared. Multiply that by the gross area, which is meter squared. So you're left with kilonewton. And then the unit of the force is also kilonewton, so that will cancel out. As far as the moment goes, again, here I'm introducing a dimensionless number, which I'm calling Rn. Here I'm multiplying the axial force by eccentricity to transfer that into a moment. And then here I'm multiplying the F prime S area gross with the dimension in the direction of the eccentricity. Usually it's more than that. I'm more interested in the ratio E over H, because my dimensionless interaction diagram will show these on that diagram. So these are, so instead of using moment, I'm using Rn. Instead of using the axial force, I'm using Kn. And here I am doing that for each reinforcement ratio. So this one represents the reinforcement ratio of 1%. This one represents the reinforcement ratio for 2%. This one represents for 3%, and this one represents for 4%. Now, the one that I'm showing right here, this curve, which is for 0.0176, is the reinforcement ratio that I actually used in this previous example. Another definitions that you will see that this is only for F prime C 28 megapascal, and this is only for Fy 420, and this is only for gamma equal to 0.74. So now what is gamma? Gamma is defined as this distance right here, which is the distance between the reinforcement, which is usually a ratio of the total length in the direction of the eccentricity h. So if you have a gamma, let's say 0.8, and you have an F prime C of 30, you cannot use this dimension. You cannot use this. Okay. If F prime C is 22, for instance, and F 420, and gamma is 0.74, you still cannot use this dimensionless interaction. For you to be able to use this interaction diagram, all the stars have to be aligned, which means you need F prime C 28, you have to have Fy 420, and you have to have gamma 0.74. Now, the dimensionless interaction that you will see in the handbooks actually looks something like this. Here I'm giving you two different examples. One is for a rectangular column and one is for a circular column. Now here again the same definitions. F prime C here is 28, Fy is 400, but gamma here is 0.8. So in my previous example I will not be able to use that by itself. Okay. If I have a circular column, and again this is only valid for this arrangement of steel. So if I use another arrangement where steel is distributed in this fashion, I cannot use this. Okay, so this is only for this distribution of steel. And for the circular columns, it's the same thing. Gamma again is 0.6, right? And here is gamma, and it's the outside distance, I guess, minus the cover. Okay, for the case of the circular columns. Again, if it's anything but 0.6, you cannot use this dimension, this interaction diagram. Here actually you can also see the radials of E over H. That will help you when you do the interpolation. Here the reinforcement ratio is going all the way from 1% up to 8%. So when you calculate the values of Rn and Kn, they are actually small squares that will actually help you in finding the values that you want, and I will show that in the following example. But the takeaway from this, each interaction diagram is only conclusive for the dimension that is shown right here. Okay, and I will talk about it a little bit more during the examples. So let's go for another example. Here I have a tied column. Cross section as shown is to be used to support the following. So he's giving me the dead load at 600 kilonewton, live load at 900 kilonewton. The moment dead load is 200 kilonewton meters, live load is 250. F prime C given 28 megapascal, and Fy is equal to 420 megapascal. What he wants the reinforcing bars to be used by referring to the dimensionless interaction diagram. So he does not want me to use the method that we used in the previous example. So what do I know about this column? I know this to be 60 centimeters, so this is given to me. I know this to be 40. Here I'm choosing the distance to the center of the reinforcement to be 6 centimeters, which I usually call my D prime, if you will, in this case. Or the cover, it's usually the cover, and up to the center of my reinforcement. So first of all, I need to figure out what type of interaction diagram I want to use. So for that, I need to figure out what gamma is. Okay, now gamma is going to be, again, H is 60, and we take from it 12, divide that now by 60, and you will get gamma of equal to 0.8. So now I need a figure in which gamma is equal to 0.8. I need F prime C to be 28, and I need Fy to be 420. So that's the interaction diagram that I need. Obviously, I also need to find out what my P ultimate and my M ultimate is. So I'm going to use the same equation, which is 1.2 dead plus 1.6 live. So this is about 2,160 kilonewtons. The ultimate moment, again, 1.2 dead plus 1.6 live. This is going to be 640 kilonewtons. So now I can calculate my Kn and Rn. So my Kn is going to be my P ultimate, which is 2,160 times 1,000. to be in newtons. Divide that by 5, which is 0.65. F prime C 28 Newton per millimeter square. The gross area is H 600 times B 400. So I'm getting 0.495, which is 0.5. Again, since I'm using everything in Excel, okay, and I will show that. I'm using the numbers as is, but when you are I guess using a ruler or using the actual interaction diagram, you probably use 1/2 here instead of 0.495, obviously. For the calculation of Rn, the ultimate moment is 640 times 1,000 to make it into newtons times 1,000 to make it into millimeters. Divide that by 0.65, again, my phi, 28. This is becoming h squared, which is 600 times 400, because area gross is b times h, another h, so that will be my h squared, and this is 0.244. I probably here will use 0.24 if I'm using a ruler or if I'm using an actual interaction diagram. Okay, now here I'm telling you by interpolation I found this to be 0.0269. From it I was able to calculate the area of steel, so I multiplied this ratio that I got from the interaction diagram by the gross area to get this. So this is times area gross, and you will get this area going to the tables, and you will see that I need 10 by 30. And since I have them distributed into 2 rows, this will take 5 and this will take 5. So let me show you how I got this interpolation right here. So now I have this interaction diagram that I used. Again, I looked for gamma equal to 0.8, Fy 420, and F prime C 28 megapascals. Here I have the different reinforcement ratio, 1%, 2%, 3%, and 4%. So now I found my Kn value to be 0.5, okay, which is right here. So at 0.5, extend all the way up to here. Then I also calculated my Rn to be 0.24. So I have this point right there, extend, and this intersection is the reinforcement ratio that I am requiring. Okay, so now here I'm doing an interpolation between. Now this point is falling between the 3% value and the 2% value. So, and that's how I did the interpolation. I just measured the distance between this one and this one. So that distance is equal to 1%. And then I measured the distance from here to here. And that distance I divided by the total distance and multiply that by 1% and added that to my 2% to get my 0.0269. Obviously, you're not going to get 0.0269. You're going to get almost like 0.027. But again, like I said, I've used my Excel spreadsheet to get the actual values, and that's why I used this one. Come to think of it, this actually should be 0.027. And that's actually what you're going to get if you're using a ruler. But if you're using some software, you might get actually some stuff more accurate than that. So that's what I got for this example. Now I'm going to move to a different example. Here I have again a tied cross section. Again, I'm using this type of arrangement for my steel. Okay. Again, I'm giving you the dead load and live load for both the moment and the axial force. I'm giving you my F prime C. I'm giving you the Fy. He wants what is required is the column dimension to be used by referring to the dimensionless interaction diagram. Here I'm going to assume that I'm going to use the 3%. I'm going to assume H to be 60 and see if that works. Okay. And I'm going to assume that the distance to the center of this reinforcement is 7.5 centimeters. So for that, again, I have to calculate the ultimate axial force and ultimate moment, 1.2 deads at 1.6. I'm getting these values. From that now I can calculate the eccentricity. Usually in the interaction diagram, if you start with a fresh column, you always assume the dimension in the direction of your eccentricity, because you will need that E over H value. And then By calculating that, I'm getting 0.54. Now gamma again is going to be equal to h, which again is in the direction of my eccentricity, minus 2 times 7.5 over 60, which is equal to 0.75. Now, one thing you should know that the interaction diagram that are provided in our textbook does not have a gamma value of 0.75. So you will find for that column arrangement that we need to find the design for. We only have a value of 0.7 and a value of 0.8. Okay, so what that means to you, it means that you have to do all the work that I'm going to show you right now once for 0.7, and then you have to do it one more time for 0.8. So you're going to have a value for your B at 0.7 and a value for your B at 0.8. So to get to 0.75, you do an interpolation between them, which is obviously going to be the value divided by 2. But I did not do that here, again, because I have my own spreadsheet or my own program. So I was able to generate my dimensionless interaction diagram for gamma actually equal 0.75, F prime C 28, and Fy 420. Actually, I did that. I have two programs, one is an Excel spreadsheet, which make me draw this for you. And I also have a MATLAB program that can actually do the interaction diagrams for me as well. But again, I was lucky enough to get gamma 0.75. Sometimes if you don't find the gamma, let me re-emphasize that, then you have to do the gamma that are surrounding your value that you want. So in this case, again, for the 0.75, you need a gamma at 0.7, do all that work, and then you need another gamma at 0.8 and do that work as well. Okay? So now, if you go to that diagram, again, you will have the values of E over H plotted. So you will have a value of E over H equal to 0.55 and the value of E over H equal to 0.5, which are these two right here. So this is provided to you. Okay? Again, so now we are having this dimensionless interaction diagram for the specified gamma that I need with different reinforcement ratio. And these are the E over H that are drawn on that dimensionless interaction diagram. And you know that the value that I want, the EH over value, which is 0.54, is going to be somewhere here. Okay? And since I want my reinforcement ratio to be around 3%, so I'm going to be mainly interested in this part right here. Okay? Which I will actually do for you. So here I'm just exploded this area here. So this is my reinforcement ratio of 3%. This is the E over H of 0.5. And this is the E over H of 0.55. The value that I calculated was 0.54. So that value is going to be right here. Okay. Again, I did the interpolation on this line right here. So I calculated this distance. Okay, so or measure this, excuse me, if I'm using a ruler on an actual piece of paper, then I measure this distance. That distance is going to be 0.05 long. I need 0.04. So again, by dividing that by that ratio, I'm going to get this point. I know everybody knows how to do interpolation. So once I have this point, I have two choices. The first choice, I could go, let me do that in a different color. I could go this way and get a value for Kn. Okay, so this will give me a value for Kn. Or I could go this way and get a value for Rn. Usually I go for Kn because it is, I guess, less work, right? One more or one less number to multiply by. Okay, but whether you chose Kn or Rn, you will get the same answer. So in my case, I just shown you that if you use Rn, you get 0.254. Kn will be equal to 0.475. Excuse me. But again, I'm using the value for Kn. So now Kn is equal to P ultimate over phi F prime C area cross, right? Which means now my B is going to be equal to P ultimate divided by phi F prime C Kn, which I found, times H. So I'm going to use my P ultimate as 2240 times 1000 divided by 0.65, divided by 28, 600, which is the value of H that I chosen, and the Kn value that I got, and this is giving me B to be 431. So for that, I chose to go to 450. So my B is going to be 450. So again, because I want the 3% of area steel, so this is going to be 3% times 450 times 600. This is going to be 8,100 millimeters square. So for that, I'm going to use 12 by 30. Again, this is the arrangement that I have. This is my 45 centimeters that I chose. Obviously, you have to make check also that these 6 by 30 will also fit into that column, by the way. So again, the same technique that we used, 6 times 30 plus 5 times 30 plus cover 40 plus, since this is 530, I can use 510 plus the 10, so this is 50 cover on each side, which amounts to 200, and that will be less than your 45 centimeters. So at the end, the only thing that I need from you is from this part is two things actually, is how you could actually, if I give you a values of C, how to generate a point on the interaction diagram. I will never ask you to draw the interaction diagram, but I might ask you to find certain points or certain values on that diagram based on the first example that we did. The other one would be, I would give you an interaction diagram, give you some assumption, and then you will give me either the dimension or you would give me the area of steel. So you guys, that will end this part. Have a nice day and stay safe.